So this is the module 2, the wrapper method in the feature selection family. So we don't get time to cover feature selection in details in last Thursday's class on the general dimension reduction family. So this is a reuse of some of my last year's recording explaining the details of feature selection method. So let's get started.
Then let's move to wrapper approach. We want to use a predictor to select and also to assess a feature subset, hopefully to train a better predictor by using less features. So in the wrapper approach, that predictor you're going to use are considered as a black box model. You just feed in the theta. You have to feed in the subset selected version of the x. So in the end, you have a theta. Use theta, you got p prime based, it's n times p prime feature. Use theta to select n times p prime matrix, and you just feed in together with the y, the predictor, the output, so your x and y, and you train a predictor based on the results, the learned model, and you use it to score that subset according to the predictive power of the learner trained on the subsets. And your result will vary. This is not a predictor agnostic approach, because it's really about that predictor cares about this feature or not caring about that feature, or the feature subsets. So I already emphasized many times how to measure the performance of a learner and how to search in the space of all the features. So like I told you, because of the 2 to the p search space, right? All this category of methods use some kind of greedy-based search. Greedy-based search, the most classic and simple approach is forward selection. The other is backward elimination. So what is forward and backward? Let's go to see this. Forward means, okay, I start from nothing, and from a 0, 0 vector of theta. I'm trying only the 1, 0, only the one of the feature is selected. I'm comparing all those theta cases with only there's only one in one of the elements, and you rank them, and you pick the best. So that's your current selected feature. And based on that selected feature, assuming we selected second features, and then we just go on by keeping that second features by trying all the rest. So second feature is selected, and then we try condition on second feature is selected. Should I select the first? Should I select the third? Should I select the fourth? So the cost of this search is, in the beginning, you have p positions to pick, right? To select, that's OP. And when you already select one, condition on that one, you have how many to select? P minus 1. When you have 2 already, you condition on that 2, you keep adding ones on that theta vector until at some stages you stop. You decided to stop. So that's why, so this should be class, right? It's a multiplication, yes. So p times p minus 1, p times 2 until p minus t is forward. This is called forward selection. And the backward is really just the backward from this vector. You remove one feature at a time. You rank them. You pick one of the feature to be removed. Sorry. If you do reversely, and that's the one, and then you keep removing according to the third feature is removed. You have only 3 choices to remove. This is called backward deletion. Forward, backward, they're both polynomial cost. They're polynomial algorithms because you control it, right? You control when you stop. Question here? They're polynomial search algorithms. Yeah. All right. So the predicting power is okay. Now it's something very important. So you're training a classifier, right? So this is actually the next page. So I'm selecting theta, one of the theta, assuming it's theta, how do I label that? Maybe theta I. And I get xpi, let's just use that xpi, n times pi. And I try to learn a function, and y. I try to learn a function f, right? Assuming that's called fi, because it's one of the model, right? The only one of the model. How do you evaluate? You need a validation data to evaluate what's the feature performance for now. So this is one of the strategy I ask you to implement in the homework is called train validation test pipeline. You train the model on the train float or train part. You evaluate different models on the model part. And after you already selected, you decide how many features, who is the best theta star. So this, you use this to select theta 1, theta 2, until theta I, or maybe theta t. It gives you a best theta star. And then you retrain the model using the theta star to get the f, and use that f to evaluate on the test data. You can't, I'm so sorry, you can't touch the test data when you're trying to do the model selection. Test samples are not to be touched in any way, in any like fitting step or hyperparameter tuning step. No, whenever you try to select something to learn a function, you can't use the test samples at all. And this actually tries to separate model selection versus model assessment. I'm going to explain that actually just in a second, but keep that in mind. Train validation test. Now we are moving from the train test we used to trying to tell you. Actually, the train test we did before is the train validation step. Okay. Question here? Oh, sorry, I totally imposed my writing on it. Yeah, I'm going to clean this up. Let me remove my writing. Yeah. So for each feature subset, you train the predictor on the training data. You select the feature subset which perform best on the validation data, and you repeat an average. You want to reduce the variance. This is more like a bootstrapping approach. You can in the homework second programming. So this uses a train test or train validation strategy to do the model selection, right? But you can actually combine them together, perform cross-validation, because that's a more stable strategy to do model selection. And in the end, you retrain the model on the whole M1, M2 data, and you apply the learned model on M3 as your testing generalization error. Question? actually in a lot of even state-of-the-art papers, they did something wrong. They're performing cross-validation on whole data, then only report cross-validation errors, which is actually not correct. And you have to separate the model selection and the model assessment. Testing data could not be touched at all. Okay, so yeah, this is more like what I just did. You have theta 1, 2, 3, theta m, and on m1, m2, using m2 to select the best and pick the best to give you a theta star. Yeah, actually I should write validate. It's the same thing. Test or apply. In choose, it's trying to do validation. And however, they give you the, then compare that validation error, mean validation error, if you the theta star. Question about this? All right. Yeah, this is almost the same thing. So if you do a regression, you have different, you train that specific theta, you got that beta. So because when you train, you got a fitted beta star for that specific theta, right? Questions about this? This is the training stage, right? Feeding stage. I know that the notation is a little bit confusing, but so beta is the fitted beta star, either from normal equation or from gradient descent, fitted the best on your current training data, conditioned on the theta j selected features. Then you apply that beta j on the validation data, you got prediction error, prediction loss, and you do argmin of all, you do argmin here, you got the best theta, I should have theta j, give you theta star, then you use theta star to retrain on both data m1 and data m2. And that gives you this. And this just trying to repeat all this, but you're going to understand what I'm saying here when you code that polynomial regression task. Yeah. And the one you're going to report test data is the examples you never touched. And using the beta star and also theta star, you'll learn. All right, so forward selection, backward elimination, beam search, always keep the k-best path. Not doing greedy at each stage, but I always keep the key best path that I can derive so far. This is another type of greedy, but a little bit more relaxed greedy. And there's a lot of search algorithm. I hope you already learned from the algorithm combinatorial search in the end. Question about this? Maybe steal this figure. But I'm pretty sure you're going to understand it when you implement, oh no, in this polynomial regression you don't need to select features. Yeah, forget about that. Yeah. The polynomial regression is to select the D. So you don't do feature selection, yeah. So, yeah. But the procedure actually is the same. In those cases, you really just, there's no theta anymore. You need to select the power, right? That's the power D. Okay, so we reduced the exponential cost to the polynomial cost by the greedy type of approach, or there are many different kinds. Now we move to the embedding-based approach. So embedding-based approach you already learned, which is lasso. Actually, the most classic is lasso and elastic net, or those group one norm structured sparsity-based approach. There is a huge literature behind this type of embedding approach. It's very popular. It's a very active research field in the past 20 years. Yeah, structured norm. So we only learned about L1 norm, all this elastic L1 plus L2. There's also a lot called structured L1. So if you're interested, I'm going to post a paper, summary paper. Feel free to read it. And also help to optimize it. It has a lot of optimization background behind. It takes some time to learn how to optimize this type of approach. So it's specific to that learning machine. It's perform variable selection and prediction using a single model. But you have to perform hyperparameter tuning of that lambda. And this is the homework related to regression, but in the lasso case, you need to do the same thing. So we covered about regularization path, which really is, I think that's the regularization path of L1 across all the different lambda. How did each of the feature, how did each weight vector corresponding to each feature varies from 0 to non-zero. That give you a good trajectory of the importance of the dynamics, how the features interact, or the collaboration among features to predict the output variables. All right, to summarize, you have all feature, you either use filter-based approach, and it doesn't even correlate it coupled with the filter, or you have the wrapper approach, uses the predictor as one of the evaluator to iteratively select features, with the most used are the greedy forward selection or backward elimination. And also the last approach is the embedded based lasso type of models. And actually all those three are very popular in the state-of-the-art machine learning pipelines and also toolboxes. So in practice, no method is universally better, and also feature selection is not always necessary. So that's the conclusion I want to share you.